Okay, so this is the final lecture, and what I was going to do originally for this was to make a super long lecture, around an hour 40 minutes, which corresponds to two classes. But as I was starting to make the notes, I realized that um, this was actually this is very mathematical topic, and I didn't want to dive too deep. So what I'm gonna do is I'm gonna have a surface level perspective and not go too deep so you have more time to focus on your project. So um, I know that it's like extremely close to your presentation um, presentations because that starts next week. So it's unlikely that you'll be able to implement hash families into your project, but it's just a intellectual curiosity also. So what is a hash family? So one thing that well, let's just take a particular scenario. So let's just say we have a covering array right here, and what I'm gonna do is I'm just gonna pick these three columns, and I'm gonna copy and paste them over here. And what we can guarantee now is if we have just this array right here with three columns in it, then I know that this is a covering array because I picked three distinct columns out of the array. But suppose instead I picked um, I picked this one, and I picked the same one again. The first one I picked twice. Well, when I have it over here, well, look at these two columns. Well, look at the first two columns right here. I'll zoom in a little more so it's easier to see. So look at the first two columns. Let's just say I ordered them by their column index or something. But it actually doesn't even really matter how I order it. I know because I picked a column twice that I have a duplicate column, which is fine, but we cannot cover all interactions because of that involve these two columns because there's a duplicate. So in these columns I'll see 0, 0, 1, 1, 2, 2, etc. But I'll never see something like 0, 1 because it's a duplicate column in those two. In the other pairs of columns, because they're different, I will always see all pairs because that's what we saw in the original array. But if I pick the same column twice, I'm not gonna cover all interactions. So if we pick t different columns, then actually this can be amended to be at most t, but we might as well just say t. We want to get as many columns as possible. So let's just say t. Then if the covering array has strength t, then every interaction is covered because you pick t different columns. It's just the same idea. But if we pick some columns repeated, not all interactions are covered. So what we can do is to try to get a lot of columns possible, or at least if we possibly can. And what we can do is the following. So I have like a narrow array right here. And what I'm going to do, and let's just say that this is the pattern array that I mentioned right there. And let's say we have a covering array right here. And the covering array has columns 1, 2, 3, 4, up to k. And each value in this pattern array thing is from the set 1 up to k. So the values in the pattern array correspond to the columns of the covering array. And I should say that this actually is a covering array. So what are we going to do here? Well, let's just say in this position, whatever it is, let's just say, okay, maybe here. Let's just say that this is value I. Then what I'm going to do is some operation, I'm going to call it x with a circle around it. And what are we going to do with this? What I'm going to do is I'm going to make a substantially taller array, but a larger number of columns. And so what are the properties? The number of columns here equal the number columns in the pattern array. And what are we going to do? Well, at this position, let's just say this value I that we looked at is in row J of the pattern array. Well, what are we going to do? Well, we're going to, in that corresponding position, replace that position with column I, let's just say this one, of the covering array. So if that value was right here originally, well, I'm going to copy and paste column I of the covering array here. And we can do this with any array that we want to, but it's just whether or not the resulting array is a covering array. It may or may not be one. So what we're going to talk about here is something called a hash family, which is a sufficient criterion for when this big green array really is a covering array. So what is this perfect hash family thing? So there are numerous types of hash families that you will deal with. A hash family in general is just any array, but the key here is the word perfect. So hash family is literally just an array. It's just another name for an array based off of some historical terminology. But the word perfect here is the property that we want. So if we do this operation and the pattern array is a perfect hash family, then the resulting array is a covering array. So how does that work? Let me turn my sound on. Okay, so how does that work? Well, I have the definition here, but it's easier to look at the picture. So the order of the 4 values here is slightly different than the covering array case, and that's because of historical reasons. So the number of rows n is still here, the first one, but now the number of columns comes second instead of third. The number of values here is v, and the strength here is t. And v here corresponds not to the columns, but corresponds to the number of values in rows. So in the covering array case, if I had v equal to 3 or something, then that means every column had 3 possible values. In the perfect hash family case, or I guess in the hash family case, each row has 3 values. So in this case, in this array, we have v equal to 3. So if we look, each row has at most 3 values. And so we see that there are 6 rows and 12 columns. 3 values per row, which is fine. And what is the 3 here for the strength? Well, that is looking at any 3 columns, let's say these 3, and we're going to look at the values in each row one at a time. And we're going to ask the question, are all the values different in these 3 columns in this row? Well, we see we got a 0, 0, 0, so they're not all different. And what we require is that we have at least one row that has this property. It's not that we have every possible ordering or anything. We just have some row with all distinct values. So the first row doesn't work. Let's look at the second row instead. Well, we have 1, 2, 1. We have a repeated 1 here, so that doesn't count. Now we have 1, 0, 2. Well, that is 3 different values, so that's good. And I don't need to check any other row. In this case, we have 1, so that 1 there is the lambda. So the number of times this separation of different values occurs. So when we have all distinct values like this, that corresponds to being separated. So in covering array land, a interaction is covered in the perfect hash family world, a set of columns is separated. And one thing we should note is that we could have any ordering of the three values. So it could be 0, 1, 2, 0, 2, 1, 0, oops, 1, 2, 0, 1, 0, 2, 2, 1, 0, 2, 0, 1. As long as we have some row with all distinct entries in them somewhere, in any choice of three columns or T columns in general, then it's a perfect hash family. Yeah, and in this particular case, this one is optimal in number of rows. So there's for 12 columns, 3 values, and strength 3. There's no 5-row perfect hash family, and that's something that I've proved uh, a little bit ago. But it's not optimal in number of columns. So in this case, you can actually go to 13 columns. Um, and I'm not sure if you can get to 14. That's actually still an active area of research, but I'm pretty confident 13 is the maximum for these parameters. So a commonly discussed quantity is the perfect hash family number. So this is called the perfect hash family number. So it's kind of like the covering array number, and it's just the smallest number of rows for which a perfect hash family exists. So it's very analogous, except the two differences are that the V corresponds to the number of values in the rows, and the strength corresponds to separation of columns, not covering every interaction or something. So we actually know a little bit more about perfect hash families um, than covering arrays, especially for string 2. So for string 2 and lambda equal to 1, we happen to know the exact answer in general. So it's this quantity. So the idea here is let's just list out all, let's just say we have n rows here. And what we can do is let's just list all v to the n possible columns. Just list them all. No thought or reason into picking any choosing columns. We're just listing them all out. Well, let's just pick any two columns. Well, let's see. Well, since the columns are different, so these columns are different, well, that means in some position, well, they could agree in a lot of positions, right? So we can have a lot of positions agree, but in some place, they must have a different values, like 0, 1 or something. So that means that it is a perfect hash family of strength 2, because no matter which columns you pick, they must disagree in one position, because we never listed a duplicate column. So that means that the number of columns we get k is v to the n, and if we take logarithms, we get log k over log v is equal to n, and since the number of rows must be an integer, we take the ceiling of this, and that's what we get here. For lambda equal to 2, what you can actually do for strength 2 and 2 values, so the previous one works for any number of values that you want. Here, if we happen to have exactly 2 values, the idea is for this one, we list all columns with an even number of ones or zeros. It doesn't really matter. So why does that work? Well, if we have 2 columns, well, they must not be the same. Well, if they have an even number of ones, these must disagree in at least 2 positions, which means that these 2 columns are separated twice. So that, and by listing all columns with an even number of ones, we list half of all the columns. And you can actually show that you can achieve, oh, that should not be -1. That should be +1. That's my mistake. Yeah, it should be +1. I can't have fewer rows with higher separation. I need more rows. Um, yeah, and in general, we don't know the answer because this is actually a really wide open question, a research question. Because it's connected to something called codes, which I'm not going to get into, but it's very wide open and no one knows the true answer for all k. So why study PHFs in the first place? Well, we get this amazing theorem, which is incredibly useful. So I wouldn't look too much at the details of what these are. These are just the parameters that are chosen here are just to make the two arrays compatible with each other. And the idea is replace a value I in the perfect hash family with column I in the covering array. It's exactly the same idea as we had before. But the amazing thing that hasn't really been explored at all, and I really want to see at some point, is look at the indices, the index. So if the covering array has everything covered at least lambda times, and the perfect hash family has everything covered beta times, then the covering array you get at the end has everything covered alpha times beta times. And you can go through the construction and see that that's the case. If you replace everything with column I, well, pick any t columns. Well, the perfect hash family has beta places where everything is separated, and in each one of those are t columns of the covering array, and the covering array, by assumption, has everything covered at least alpha times. So for each one of the separations, we have alpha covers. So beta times alpha. And the only real thing that we pay here is that the number of rows is much bigger. It's the number of rows in one times the number of rows in the other. Oh, yeah, that's right. But the thing here is that we still maintain the strength of the covering array, and we still maintain the number of values in the covering array. After all, we're just copying and pasting from the covering array into the new one. But the number of columns that we get is based off the number of columns in the perfect hash family. So the goal of PHFs is to have very large number of columns. And in fact, some of my work in finding really big PHFs in terms of number of columns has actually given the best constructions of covering arrays for some parameters. So that's what we want. Very large number of columns and a low number of rows. And so I'm just going to go quickly over some things that are known. And one thing that I should also note is that um, the number of columns grows approximately log k, or I should say theta log k, in general. So just like the probabilistic method with covering arrays, we get exactly the same thing with perfect hash families, but the constant is much lower with perfect hash families than with covering arrays. So for specific parameters, there's actually quite a bit known. So in specific scenarios like this one, where we have strength 3 and 3 rows, excuse me, um, and actually there is one for 2 rows and 3 columns. Um, and there's some result on that too. With 3 rows, this is optimal for the number of columns that you get out of it, but you get approximately v squared in terms of the number of columns that you get. Yeah, okay. So there are some where you can have a general scenario where the number of rows is quite a bit is pretty small relative to the strength, and in some cases that is optimal, but you only get a linear um, bound in terms of the number of columns. So in some scenarios like this one, you can get v squared, so it's the square of the number of values that you have. And in some cases, if the number of rows is sufficiently small, then you can only get linear. So the question is, well, where's the boundary in between when you go from linear to something nonlinear? And that's a recent result of mine and some other folks about that. But I won't go into that because that's actually quite complicated to even explain. And I can give you the paper reference if you want it. Um, so there are some other works where if you have v being a prime number, so like 50, 59 or something, so like a sufficiently large prime, then there's a lot of results on like if you have 9 rows in strength 3, then there's a covering array which is like v to the fourth number of columns or v to the third or something. So if you have a relatively large number of rows, you can actually increase the ratio between the number of columns and symbols. So if it's really small, you get linear. If it's a little bit bigger, you get v squared or something. And if you go bigger, you can get like v to the 3, v to the 4, then it just keeps going up the more rows that you give. And there's a lot of recursive constructions here. Again, I can go down into the weeds with all the recursive constructions, including some recent results of mine that improve some recursive constructions, which take literally an entire slide to state what the theorem is. But I'm just going to leave this like this. The key here is that a lot of these results work with the finite field when we were talking about that before. And a lot of the properties of the finite field allow you to I use some results from algebra or other things to give you really good recursive and direct constructions, but I'm not going to go into that. So the key here to understand is that a perfect hash family has a very similar structure to a covering array, but the criteria for being one is different in that you separate columns versus having interactions appear. So the paper we're going to read on Friday is very similar to this. It is a hash family, but the notion of what it actually is slightly different. There is a notion of separation, but it's an analog of a perfect hash family if we had something like it for a covering array. So if we want the best of both worlds, being a perfect hash family and a covering array at the same time. And what it is able to do is something called a covering perfect hash family. And what it does is using some arithmetic over the finite field again, you can actually expand one of these entries, which in the covering perfect hash family, into an entire column of a covering array. So the downside of perfect hash families, if we want to use them for covering arrays, is that you need a covering array to start with. Whereas a covering perfect hash family, you just have the array itself and no other array, which is really amazing. So that's the paper we'll read on Friday. So I'll see you then.